All right, so I'm redoing the audio for this, so this will be a little bit wonky. Anyway, this is lecture 16, Energy Equation, and the goals today are we're going to understand the energy equation and this term alpha. Alpha is kind of important, it looks kind of weird with this particular font, but we're going to talk about it, and then we're going to apply the energy equation and work a couple problems. So if you hear a glitch in the sound at around, 11:54, that's because that's the original sound, and I got to work into that. Okay, so I guess I'm waiting for my visuals right now. I don't know what I said the first time. But basically, we're going to think about the energy equation as kind of an improved version of Bernoulli. And everywhere in this where I'm going to use a 1 or a 2, so like with Bernoulli, it was like P1 over gamma plus, looks like the real thing starts, but in Bernoulli we had this. Let's talk about what's actually going on here. Okay, so we're going to think about energy in terms of control volume. Okay, and so we think about the energy going into a control volume and the energy that leaves a control volume. And so we think about what goes in, what comes out, and obviously you could accumulate what's in there. And so I'm not going to do a big detailed derivation of the energy equation because it gets pretty complicated. We're just going to think about a control volume. So here's a random control volume, any shape, and of course you can draw the shape that makes it work for you. And we've got energy crossing into that control volume, okay? And we've got energy leaving that control volume. And there's a few ways that we can kind of affect the energy that is in there, okay? We have to remember that this is a fluid, and we're thinking about the mechanical energy of the fluid. So yeah, some of you might say, well, we could heat it up or something like that. That's thermal energy, and I don't want to discount that, but that's not really what we're concerned about in this class. So what I was saying a second ago is that everywhere, this is going to be like your point 1, and this is going to be your point 2, essentially, just like it was in Bernoulli, but we're going to call this in, and we're going to call this out. Or really, we're going to call them 1 and 2, but really we mean in and out. Okay, now we have to wait for the animation. Okay, because, there's ways to kind of add to that energy, and one is you can do work on the energy. And if you want to do physical work on the fluid, one of the things we'll do is a pump. Okay, and you can imagine how a pump, if you add a pump, you can add potential energy by pumping something up a hill. You can add potential energy by increasing its pressure. You could add kinetic energy by making it flow faster. Generally speaking, pumps add pressure is really what they do. And so that is one of the primary things we're going to be worried about is the work of the pump. Now the pump has to be within the control volume. Okay, so it has to be between the in and the out, or else it's not really involved in our particular control volume. Otherwise, it's increasing the energy of a fluid that is not in our control volume. So that's something that we're going to kind of focus on as we move forward. And okay. So you can also take energy from the fluid similarly with a turbine. Okay, and the cool thing about a turbine is it's just a pump in reverse. So instead of us pushing on the fluid in order to get, in order to increase the energy of the fluid is pushing on our turbine, and so our turbine is removing energy from the flow. And so that's that's pretty powerful and useful. This is how a hydroelectric dam works, or something along those lines. You have a turbine. Usually you place it at the bottom of the dam, and you take advantage of the pressure down there to turn your turbine, and you can generate power. Okay, obviously, if you remove a certain amount of power from the fluid, you don't get all that out. Okay, the last thing, and this is kind of cool, is that you also lose energy due to friction. So anytime you're flowing through a pipe or on a trapezoidal wall, a trapezoidal channel, like if you imagine the LA River, which shows up in all those things, it's a concrete thing where they drain the water from the city. You can imagine the friction from that concrete is going to slow down the flow of that water. Okay, and it's going to take some of the energy, some of the mechanical energy, and it's going to transform it into heat. Okay, so that's an important consideration, and we'll see as we go along just how important a consideration that is. I'll kind of mention it on some of the problems here, is how big that friction term can get. In fact, I'm already plotting a good problem based on that, which I think will be kind of interesting. I'm plotting, making you all calculate how much energy we lost if we had to pump water from Louisiana out into, say California, so they could have more drinking water. And it looks like at this point I had some issues moving things around, finding a good place to work. Okay, so we're going to talk about the energy going in, and we're going to call that head. Okay, so instead of describing it in terms of kilowatts or kilowatts, instead of describing it in terms of joules, we're going to think about it in terms of head. So there's going to be feet of head. Okay, so that's the head, is the energy going in. Okay, and then we're going to add whatever energy that the pump might add. Okay, and remember, the pump, the turbine, and the friction all have to be inside that control volume. Okay, so then that's what's going into our system. Now, what's leaving our system? Well, head at location 2, or really the head out. And then we're going to lose some energy due to the turbine. Okay, notice that for the pump and the turbine, these are going to have to be in the same units as the head. So instead of thinking about them in terms of joules, we're going to think about it in terms of like feet or meters. Okay, that's just kind of it's just the way we do this, and it actually makes things pretty easy. And then last, of course, we lose energy in terms of friction. Okay, so when we say out, in that case, really it's being transferred to heat. Okay, so those are our three terms that basically kind of, pump, turbine, and friction. These are the three terms that basically change this from kind of the Bernoulli equation into an energy equation. Okay, so here's our head. Now notice it's slightly different than the Bernoulli head, but only slightly, and in practice it's not really that different. Okay, so then we've got the head of the pump, HP. Okay, usually that's going to be in terms of like feet or meters. Okay, now we've got head at 2, or the head leaving the system. So again, it looks a lot like the Bernoulli. Okay, and we're going to talk about that bar in a second. Okay, and notice we're using everything as heads. Okay, so we've got head of the pump, head of the turbine, and now head loss due to friction. So I know you wanted it to be HF, but unfortunately it's not. So it's just head loss. And you'll see why. We're going to split that apart later. Okay, so you see the two terms that kind of look like Bernoulli, but they're a little bit different because they've got a little alpha in there. Okay, here's the alpha. And they've also got a bar.
Line over the V.
Okay, so the line over the V stands for the average velocity. Okay, and so there's a reason for that, and it's because the energy, when we did Bernoulli, we just kind of took 2 points on a line. Okay, and so there was only one velocity that mattered. However, when we're dealing with a control volume, it's the energy going into the control volume. So it could be an opening, and you can imagine that the velocity has a profile. Okay, so there's not just one velocity, there's a velocity over that whole opening, which is totally annoying. But we don't want to have to deal with that. We don't want to have to integrate. Okay, so normally you would have to integrate all of that in order to kind of drive at, what is the total energy going in. Okay. Okay, but this particular thing doesn't need streamlines. Okay, the nice thing about the energy equation is we don't need points 1 and 2 to be along a streamline. They just have to be on opposite sides of a control volume. One has to be where the flow is coming in. One has to be where the flow is coming out. Okay. So I can't believe I'm not talking about this alpha right now. Okay, notice that all these terms in this equation all have units of length. Okay. And that's their whole purpose, and that's kind of the beautiful thing about them. And I don't know what I was doing when I made these marks. Okay, we should be talking about the alpha and the bar. Okay, I think maybe that's what we're going to do right now. Okay, so V bar is the average velocity, okay, or the mean velocity over the opening. Okay, or the entrance and the exit, okay. And we prefer to use that than to integrating. So here you go. So here's an entrance, and of course you've got all the flow coming in, and usually it's parabolic or something along those lines. So here's a control volume. Okay, we can imagine that the energy for that, because energy usually goes as V squared, so it's just annoying to have to, integrating that would be difficult. So instead we're going to use V bar. Okay, so V bar, I've kind of drawn just an approximation for really with laminar profile. And you can see that the V bar looks like it's about half of the V max maybe. So normally we would have to integrate this in order to kind of like get at the total energy going in. And nobody really wants to do that. So what we do instead is we build in this little alpha guy. Okay, and the alpha basically makes it so that we don't have to integrate. Okay, it's a replacement for that process. Okay, so then you're like, okay, well, what does alpha mean? Okay, what is it? How do I solve for it? Okay, and so here's how we define alpha. Okay, and so, well, we have alpha because the flow is not uniform. Okay, it's got a profile. We would normally have to integrate, and we don't want to do that. Makes me, watching myself do this makes me think I'm a little bit wordy. Okay, so alpha is defined, so that's the triple equals means it's defined as integral over that area of the velocity cubed dA, okay, divided by the average velocity cubed. Okay, so basically we don't ever want to have to do that to figure out what that is. But luckily there's a nice rule of thumb based on what
this should go in your notes. It's kind of important.
Okay, here we go. So it's
got really two possible values.
Okay,
one is 2.0
for laminar flow. For laminar flow in pipes. Laminar flow in pipes. Okay, and it's 1.05 for turbulent flow. Okay, and this we're just going to make equal to 1.0 because it makes our lives easier, and this is kind of the standard thing. Okay, for turbulent flow in pipes. Okay, because this is a common, and because usually you're going to be dealing with turbulent flow almost always. A lot of times people will write this section right here. They will just write this as P2 on alpha plus Z2 plus V2 squared on 2G because they just don't feel like writing the bar right there. Okay, so a lot of times people don't feel like writing these two bits. Okay, because if alpha is 1, well, obviously, you don't have to write it, and, the average velocity is usually the only one that's given. So a lot of times you will see this written without those two things. For this class, I'm going to include them just for completeness. Ultimately, you'll probably get to a point where that's not really critical. Okay, so we want to talk a little bit. There's my problem right there. Okay, so let's move and let's work over here. Okay, so we'll be a little out of order here. Okay, so let's zoom in so I don't want Godzilla letters here. Okay, so let's talk about power. Okay, so power. Okay, now for this course, I'm going to use W dot. Okay, it's typical to use a capital P, but the problem is power and pressure become confused. In fact, if you look at some of my old homework, a lot of times I have used that. Okay, so I want to think about a pump. So here's a pump. Okay. And the pump is inside the control volume. Okay, so it's inside the control volume. So somehow the pump is supplying energy to this fluid. Okay, now we are supplying energy, so the pump is supplying power to the fluid. Okay, so this would be called, I guess, W dot. This is for the pump. Okay, and I don't know what to call this. Maybe this is W dot user to pump. Okay. And so basically, the pump is going to supply a certain amount of power to the fluid. but you are going to have to supply more power to the pump, right? Because the pump is not 100% efficient, right? Some energy is going to be lost to heat or whatever else it might be. Okay, so the way we define that is we say, okay, well the power of the pump, okay, that has an equation, gamma HPQ. Okay, so this is the gamma of the fluid. This is the head of the pump, and pumps are rated by head. So you will see this. This is very common. It's a 100-foot pump or whatever. So and then the flow rate. Okay, so obviously if you're going to add, the more fluid you're going to add, the higher the flow rate to raise the fluid, say 100 feet, well, you're going to need more power. Okay, so if you how much power do we supply the pump? Okay, so if we just said W bar user to pump. Okay, that's pretty ugly. Then we have to think about this. And so there's going to be an efficiency, and that's going to be like an eta. Okay, so it's kind of like almost like a cursive N with a long leg to it. And it's basically this same thing, gamma HPQ, and we're going to divide by eta, okay, where eta is the efficiency. Eta is the efficiency. And it's going to be between 0 and 1, okay? So I never remember this formula, okay? I can never remember it. And the way I do it is I say to myself, okay, the pump, serves out, 100 kilowatts. I'm going to need to serve out more than 100. So do I multiply or divide by the efficiency in order to get, how much I need to supply? Okay, and that's how I do it. Because in a second, I'm going to change all this, but I'm going to do it for a turbine. Okay, so we're going to change this to a turbine. Now instead, we've got almost the exact same problem, right? But now I've got the work of a turbine, okay? And I've got the work user from turbine, okay? And so here's a turbine, and it's sitting right in the middle of the flow, and instead, the flow is doing work on the turbine. Okay, basically the flow is causing the turbine to spin. Okay, and then out of that, we're going in the opposite direction. So now we're getting W dot turbine to user. Okay, and so again, there's going to be energy loss between this step and this step. Okay, so there'll be an efficiency there. Okay, so the easy one is the work of the turbine is gamma HT, Q. Okay, that's the easy one. Okay, the more difficult one is the work user from the turbine. So if we pull out 100 kilowatts from the fluid, so if the fluid loses 100, we're not going to get all of it. Gamma HT Q. And then again, so if it's 85% efficient or something like that, well, then we're only going to get 85% of that out. Okay. And so this one, again, I don't memorize this. I just think about it. Okay. This will not be on your sheet, on your FE sheet, although I guess you're going to be able to use whatever you want for these tests probably because I can't stop you. So we should, yeah, so that's, whatever. I recommend thinking about this and trying to understand how this works, okay? But that's gamma times the head of the turbine times the flow rate times the efficiency, okay? So I recommend if you just kind of think about this, it will make sense to you, okay? And the same with this one. And that's a better way to remember it long term. All right, so that being said, I'm going to go over and we're going to work this example problem, which I set up before this all. Yep. What a jerk. What a jerk. What a maroon. All right. So we've got this case right here, and somebody's really impatient. They have this thing, and so they've got a tank, and they're drained. So this is, example problem 1, or whatever we want to call this. So they've got all this water, and I guess I didn't say it was water, but let's let's just consider it water. Okay. And so it's draining out, and it's going from up here, and it's going out that way. Okay. And for some reason, it wasn't going fast enough for whoever owns this, so they put a pump in right here. Okay. Now, you could obviously put a pump in, and you could pump the water uphill if you wanted to, if the pump were strong enough. But this particular question, basically, they wanted the water to go out faster, presumably. They wanted it to go out at this flow rate. So we want to know what is the power supplied by the pump to the fluid to produce this flow rate. Okay, so basically the pump is going to cause the fluid to go out faster than it otherwise would. Okay, it would be interesting. We could work the problem the other way. One important distinction between this and the Bernoulli equation is that position 1 and position 2 on Bernoulli don't matter. But on this, it has to go from 1 to 2. Okay, so in this case, we need to pick a 1 and pick a 2 that are going to work for us. Okay, so I want to remind us before we move anywhere too far, too fast. Okay, I want to think about our tools. Okay, tools. Okay, and here are our tools. I thought I'd written these down, but what do you do? Okay, so tool 1 is continuity. Continuity. Tool 2 is geometry. 2-3 is, well, I can't remember what 3 is. I can remember 4 is Bernoulli. Oh yeah, this is hydrostatics. Hydrostatics. Okay, which is basically manometer equations. And 4 is Bernoulli, and 5 is momentum. Okay, these are our tools. And we are at this point going to, especially because this is the point of this lecture, we are going to eliminate Bernoulli. And we're going to replace it with energy, okay? There's no reason to use both, okay? Bernoulli can be thought of as the inviscid version of energy, okay? It's the part where there's no energy gain or loss. But we're now dealing with gain or loss because there's a pump in our control volume. Okay, so let's define our control volume. Okay, here's our control volume. Okay, carefully chosen. Okay. Notice the pump is within the control volume, so we have to consider it. Okay. Now, what I'm going to suggest to you is that we need to think about what is going to be our master equation. Okay. And one thing we have to think about is, well, what are we looking for? We're looking for W dot for a pump. Okay. So we're saying is W dot pump equals what? Okay. So the equation for that is gamma HPQ. Okay, so HP is what we need. We know Q, we know gamma. Okay, so there's only one equation that has HP in it, and that's our energy equation. So that's going to be our master equation. Okay, all of these other ones are just going to be there to help us out. Okay, I don't know if we need continuity or this is a really ugly continuity, or geometry. Okay. So it seems unlikely that we're going to need momentum because momentum those are for problems that ask for the force on a moving fluid. So this seems unlikely. Hydrostatics, we're not going to use hydrostatics here because everywhere in this problem the fluid is moving. So we're not going to use that. Geometry, well, we've been given these two heights, so it seems likely we're probably going to need to use that. Continuity, maybe. I mean, we do have this, right? And we have a flow rate, so we might need to use that, okay? But let's start with what I'm going to assume is going to be our master, which is this energy equation. Okay, so let's go ahead and write it out. P1 on gamma plus Z1 plus alpha V1 squared on 2G plus HP plus... equals P2 on gamma plus Z2 plus alpha V2 squared, oh, I forgot my bars, over 2G plus HT plus HL. Okay, so it's a big equation. And now I think maybe you can understand why we learned Bernoulli first. Okay, so one thing we need to do is we need to pick our points. Okay, this is going to be our master equation, we're assuming. Okay, that's our master. Okay, and we need to pick our points. So I'm going to go up here and let me see if I've got a nice color that's going to show up. Okay, I'm going to pick a point. Now, it doesn't have to be along a streamline, but I'm going to pick this point right here on the surface. Okay, I should be on the surface, not like, okay, let's make it really big. Okay, and I'm going to pick this point right here, too. Okay, and I picked those 2 points for a few reasons. Okay, one, both 1 and 2 are exposed to the atmosphere. Okay, by being exposed to the atmosphere, that means the pressure here is PATM, and the pressure here is PATM. Okay, which if we assume gauge, they're going to go away. Now we could just make them whatever we want because they're both on the opposite side of the equal sign, so it's going to cancel out. Okay, so that's pretty good. Okay, we're pretty happy with that. Okay, so we picked those 2 points for a few reasons. One, we have atmospheric pressure. Two, the pump is between 1 and 2. Okay, so that means that we can solve for this. Okay, so if I'd picked a point 1, say I'd gone right here. Well, 1 would be fine, but if I chose 2 right there, then I've changed my control volume, and the pump is not included in it. Okay, so we don't want to do that. Okay, so, all right, the Z's. Well, Z1 and Z2 are known. That's another good reason to pick them. Okay, and so we're going to make Z2 our 0. Well, we'll use the actual Z's. Okay, so Z1 is going to be 20 meters. Okay, and Z2 is going to be 40 meters. Okay, it doesn't really matter as long as there's 20 meters in between the two of them. Okay, we could have made Z1 0 and Z2 20, and algebraically it would be the same. Okay, so the next thing we have to do here is we have to look at the velocities. Okay, and velocity 1, well, this is a big old tank, right? So because it's a big old tank, we're going to use a little continuity here. Well, let's do a little continuity on the side here. Okay, so let's give myself some space. Let's go up here and do continuity. Okay, this will be an aside for continuity. Let's zoom in. So that son of a. Okay, we're going to zoom in. Okay, I'm going to do this on the side. We use white. Continuity. Okay, so continuity says Q equals V1A1. Oh, no, I want to do this at 2. Let's undo that. V2A2. Okay, I'm going for the little pipe because we know its diameter. Okay, so my Q for this problem is 7.85 CFS. Okay, V2 is what we're looking for, and A2. Well, this is actually going to be the average. Okay, we haven't really been, so pi times 1 meter squared on 4. Oh, 1 meter. Give me that eraser. The erasing tool on this is very imprecise. Okay, and it doesn't seem to really want me to do it. Okay, there you go. Okay, so if we go back here, come on. Okay, give me that. Okay, then we can say from that V2 is 10 meters per second. Okay. Now what about V1? Okay. I worry about this only because I didn't get to teach you guys enough of this. But so we got V1A1 equals V2A2. Okay, and these are average velocities. So in this case, V1 is the velocity that this surface is going down. Okay, so V1 is going to equal V2 times A2 over A1. Okay. So we'll notice that A2 is small relative to A1, large. Okay, when this happens, okay, then V1 ends up being small, okay, approaching 0. Okay, so anytime you have a reservoir, lake, tank, etc., V at the surface equals 0. Okay. And it's because the ratio of these areas is very big. Okay, so try to imagine, if you went out to Lake Tahoe, and you were like, I'm going to drain this whole lake. So here's Lake Tahoe. You're like, I'm going to drain this whole lake. And so you're kind of clever about it. And so, you put your hose at the bottom because there's the most pressure down there. But your hose is a it's a garden hose. Okay, so imagine in that case, how fast is the water going to be coming out? Okay, well, it might come out really fast. If you get really down at the bottom of that lake, you might get it coming out really fast. Okay, but the surface of that lake is going to be going so slow that it's going to be approximately equal to 0. Okay, and that's what we're going on in these problems. So down here, we're going to assume that V, let's zoom in here. We're going to assume that V2 here is 0 because it's a reservoir. Okay, which is nice. V1, on the other hand, we now know is 10 meters per second. I'm going to put that up here. V1 equals 10 meters per second. Okay, that way we won't have to zoom back up. Okay, so we have to deal with the alpha. So we'll deal with the alpha. That'll be, let's go ahead and deal with the alpha right now. Okay, alpha. So we know from my notes earlier, if we go over here, we'll just deal with it down here. So it's going to depend on these things, okay, whether or not it's laminar or turbulent, okay? So what we're going to do here is we're going to say, well, we need to figure that out, okay? So it's based on, laminar versus turbulent is based on the Reynolds number. So V times the diameter of the pipe divided by nu. Okay, that's a nu, not a V. Okay, so we're just going to I'm going to kind of show you how this is just kind of a back of the envelope calculation. People get really worked up about sig figs on this, and you should not. Okay, I'm going to tell you 2 significant digits on this calculation, and you'll see why in a second. Okay, 10 meters per second. Okay, the diameter of the pipe is 1 meter. Okay, and the viscosity of water, again, you could get all worked up about the temperature. We're just going to assume 20 degrees C, so it's about 10 to the minus 6 meters squared per second. Okay, that's kinematic viscosity. Okay, so the Reynolds number here is 10 to the 5th. Okay, I have 1 significant digit here. Okay, 1 times 10 to the wait, that's 10 to the 7th. That's not even right. Yeah, it's 10 to the 7th. Okay. Okay, now remember that for pipes, the transition in pipes at RE is approximately equal to 2,000 to 4,000. Okay, so 10 to the 3rd, right? We're at 10 to the 7th. Okay, we're crushing that. Okay, not even close. Okay, we're 4 orders of magnitude bigger than that, so this is super turbulent. Okay, which is good. Okay, and I think that this hopefully can show you why, usually when calculating a Reynolds number, we just care about transitions. Okay, so 2 significant digits is all you ever need for this. Okay, right now for transition, you probably only need 1, whether or not it's turbulent or laminar. But later on in the class, there will be a time when 2 significant digits will be useful. Okay, so usually we'll do 2. So in this case, I guess it's 1.0 times 10 to the 7th. Okay, if we want 2 significant digits. Okay, so it's turbulent. Okay, and I think you should be able to see that it's going to usually be turbulent because the viscosity is so small. Okay, and it's in the denominator. Okay, so in order for it not to be turbulent, either you need a different fluid, so the viscosity is different, or you need really small velocities or really small length scales. Okay, so so think about that. Okay, you can actually plug some numbers in there and play with it if you want. All right, so we're going to go back over here. So alpha here is going to be turbulent, which means essentially that we're going to get rid of it. Okay, we're going to get rid of that because the flow is turbulent. So we're going to assume that alpha is 1. Oh, I forgot that was the whole point of that, right? So if it's turbulent, we're going to get an alpha of 1. Okay, so there you go. So now this is looking tractable, okay? And then we're going to go over here, and we're still moving from side to side, and this our master equation. And so the pump, this is what we're looking for. And then this turbine here, well, we don't have a turbine, none. Okay, and the head loss is defined in the problem it's given as 7v squared on 2g. Okay, this is a common way to write head loss, and we will kind of get into how we get that 7, but it's almost always a function of v squared on 2g. Okay, so that's the head loss in the pipe. We're going to assume for this problem that there's no head loss in the tank, which is mostly true. There's actually a head loss in this entrance, but we'll deal with that later. Okay, so let's clean this up. Okay, so Z1 is 20 meters plus V1 squared on 2G, 10 meters per second squared on 2G, 2 times 9, 8 meters squared. Okay, plus HP equals P atmosphere. Okay, that's 0, so we're not going to worry about that. Z2 is 40 meters. Why do you gotta be a jerk? Okay. That must sound ridiculous from y'all's end. Okay, and then let's see, alpha, this is gone. Okay, so this term is gone, this term is gone, and then the head loss, which is going to be 7. Okay, now this V right here, okay, this is the head loss in the pipe. Okay, so it's the velocity in the pipe, which we solved for, which was 10 meters per second squared on 2g. Okay, now you might say we didn't solve for the velocity in the pipe, we solved for the velocity when it left at 2. Well, this pipe is not changing diameter, so the velocity all along there is the same everywhere. Okay, so if we plug all these numbers in, I think all the numbers are in there. Yeah, all the numbers are in there. Well, I didn't plug G in. Okay, so we can do that, kind of. 9.81 meters per second squared. Okay, so we plug all the numbers in, we get HP equals 20.8 meters. Okay, so the pump is adding 20 meters of head to the flow, which is pretty cool. Okay, so the way I like to think about that is if you were to take this thing, if you were to take that pipe and you were to turn it, so instead of going this way, okay, you were to go this way. Okay, and assuming, if there was no head loss at all, okay, then by Bernoulli, it would rise up to the height of the top of this water. Okay, and if there were no head loss at all, now with the pump, it's going to raise another 20.8 feet. Okay, which is pretty cool. Okay, now there is the head loss, so this would tell you how much below that we would end up. Okay, and back of the envelope, 100 divided by 20. Okay, so that's 5, so about 35 feet. So we're going to lose about 35 feet. Okay, so significant, right? Definitely matters. Okay, so not feet, meters. Okay, oh, these are meters. Sorry about that. Okay, so let's go ahead and finish the problem, okay, which is that we want this. Okay, so we want, so this is how much energy the pump is giving the fluid in order to make that happen. Okay, so right now, we don't, you might care more about, in terms of like watts or something along those lines. So we'll go ahead and solve that. That's gamma HPQ. And so W dot equals gamma, so this is fluid. So that's 9810 newtons per meter cubed. Okay, the head pump, the pump in the head supplied by the pump is 20.8 meters, and the Q is 7.85 cubic meters per second, CMS. Okay, so W dot equals 1.6, okay, times 10 to the 6th. Okay, now we have to keep track of our units here. Meters cubed, get back to the original, okay. I should just start working on the next slide. Newtons times meters per second, okay. Now you should know that a Newton times a meter is a joule, and a joule per second is a watt. So my answer is that the work equals 1.6 times 10 to the 6th watts, which equals 1.6 megawatts. 1.21 gigawatts. Sorry. 1.21 gigawatts. Sorry, Back to the Future reference. Anyway, those are fun movies. Go back to them. But anyway, this is that's that. Okay, so that's how you get the power supplied to the water by the pump. Okay, so yeah, so come to office hours. Let's talk. Let's get, if you have any questions. This looks kind of cool right now, doesn't it? Got all different sizes. All right, let's do one more. Okay, we're at 40 minutes now. It's getting long, getting lengthy. Hopefully, I won't make the same mistake I made last time. I'm going to zoom in enough so that hopefully you guys can read this. Okay, so oil. I'm going to get myself a little white. Okay. Oil, specific gravity of 0.88. By the way, y'all should notice that I use SG and sometimes I use S for specific gravity. That's just because different manufacturers do it differently, and I want y'all to be ready for all of that, okay? Oh, look, I even prepared all the tools over here. And we're not going to use that stupid Bernoulli. Bernoulli, you're so like last week. Get out of here, punk. Okay. So oil, specific gravity of 0.88, flows in an inclined pipe at a rate of 5 cubic feet per second, as shown below. If the differential reading on the mercury manometer is 3 feet, calculate the power that the pump supplies to the oil if head losses are negligible. Oh, well, that's nice. No head losses. Okay, but we do have a pump, which tells us, I mean, as soon as you see a pump or a turbine, you know we're using the energy equation. You know the energy equation is going to be huge. Okay, so let's think about these equations. Let's think about which ones we're going to use. Let's use red. That's like the grading one. Okay, continuity. Okay, it seems highly likely we're going to use continuity, okay, because we've got pipes of different diameters, which usually implies that that's going to come into it. Okay, geometry. Well, we've got a whole bunch of lowercase h's and capital H's and a 3 feet. We're going to have to use some geometry. Hydrostatics. Is any part of this not, like any part of the fluid not flowing? Yes. Inside this manometer, the fluid is not flowing. Okay? So we have to use hydrostatics there. Woo, this is getting fun. We get lots of equations here. Okay, what about momentum? Okay, are we asked or told anything about forces on a moving fluid? No. Okay, so no. And you might say, well, what about the pump? Okay, well, you could think about the pump, but we're not asked for the force of the pump. We're asked about power. Okay, so when power is always, we think in terms of energy. Okay, so okay, hopefully this comes out legible. I know the last one I did, it was kind of hard to see, but let's start with, one nice thing too is that if we're not using this momentum equation, you don't have to draw a free body diagram. Okay, this is kind of nice. Okay, I'm going to zoom way in. I'm going to guess, well, I don't want to zoom that far in. You know what, I'm going to do this right under here. This is our master equation, and I want it to be somewhere where we can see the diagram. Okay, so we're assuming that our master equation, because we're looking for power that the pump supplies, we're assuming, I mean, really any equation that you use could be the master. I'm just doing it in a way that I suggest. Okay, so sorry, we had a little snafu right there, but okay, so we're going to, so the master that we're going to use in this case is P1 is the energy equation. I actually like it a little bit finer tip than that. Let's undo that. Okay, P1 on gamma plus Z1 plus alpha V1 squared on 2G plus HP. I know you think this is a lot of terms, but you're going to memorize this on accident. Okay, and that's, sad for all of us. Z2 plus alpha V2 squared on 2G plus HT plus head loss. Okay, so what I want to do now is I'm going to kind of think about this in terms of each of your, let's see, I want to erase all this business up here because that's just in the way. Okay, we're going to keep in mind that that momentum is out. Okay, and now for some reason I tried to color over it and it didn't really work. Okay, so we're not going to use momentum. Okay, we will, however, potentially, very potentially, use these other ones. Okay, so I'm going to start with red, and so I'm going to kind of go through these terms and we're going to think about how we're going to get at them. Okay, so, well, I guess before we do any of that, we need to think about our points. Where are our points? Now, in this problem, they've kind of given them to you, but I want you to think about a few things, which is one, the point of this problem is we want to know something about this pump. Okay, we're trying to get the power that the pump supplies to the oil head. So this is what we're looking for right here. So if that is the case, then we're going to need to have point 1 and point 2 be on either side of the pump. And the flow needs to pass point 1 first, and it needs to pass point 2 second. Okay, so that leads us to this, 1 and 2. Okay, now, so that then defines our control volume as this. Okay, notice the pump is in the control volume. Okay, so that's good. And the flow is going from 1 to 2. Okay, also good. Okay, now, the other reasons that we pick these points is it's about what do we know. And notice that at point 1, we know a lot of stuff. Okay, we don't know necessarily the pressure, but we can kind of get at it because there's a manometer. Okay, the same thing at point 2. We know the elevations at 1 and 2, and we can kind of get at the velocities maybe, okay, because we know the dimensions of the pipe. Okay, so let's go ahead and start kind of looking at that. Okay, so here's this first term, P1 and P2. Okay, notice that I can't necessarily get at those, like I don't know what they are. I know they're not zero. They're not atmospheric because it's inside of a pipe. But we do know that with hydrostatics, okay, we can drive at that. Okay, so I'm going to go down here, and I'm going to go ahead and solve for that. Okay, for Z1 and Z2, I'll use green for that. Z1 and Z2. Well, we can do geometry for those two. Okay, and I'm just going to do that right here because that's not going to take very much space, if it takes any at all, really. And then for these velocities, we'll use blue for velocities. This term and this term, okay, we can use continuity to get at those. Okay, and I'll do that right up here. Okay, and then we can plug all those things back in here. Okay, so then if we go back and we use yellow here, so this is what we're looking for right here. And we note that in this problem, we have a few things that are important. One, head losses are negligible. So this term goes away, negligible. Okay, and this turbine, well, there isn't one. Okay, so I'm just going to write none. Okay, so from all of that, we're going to get what we need, but we have to get all of these things on the side. Okay, so let's, I just kind of wrote in real big letters all over my workspace. So let's not do that. Let's erase all, okay, well, whatever. We can get rid of those terms. They don't exist anymore. Actually, I'm going to leave them there just for completeness. Yeah, so plus, well, now they're in yellow. Great. Plus head of the turbine plus head loss. Okay. So let's zoom in here and let's do these things one at a time. Okay. I guess we'll do continuity first. Okay, from V1 to V2. Okay. So Q. So I guess there's two ways to do this, and I'm going to show you the way that I prefer. So what a lot of people do is they'll say Q equals V1 A1. Okay, so that's totally fine because we know Q, which was 5 cubic feet per second. V1, well, we don't know that. And area 1 is pi times, what's that area? 12 inches. Okay, 1 foot squared on 4. Okay, and you get from that V1 equals, let's see, 6.366 feet per second. Okay, and V2 equals 5.465 feet per second. Okay. So there's two ways that you could have gotten at this. One, you could have done the exact thing we did a second ago. Like you could have done this, same thing, 5 feet per second, but instead of plugging in 1 here, you would have plugged in a half. The other way to do it is to just recognize ratios here, that if we're doing Q1 equals Q2, then you could say, here, I'll do this kind of up here. This is a kind of major aside. V1A1 equals V2A2. Okay, we solve for V1, so then V2 equals V1 times A1 over A2. And then V2 then, if you plug in pi D1 squared on 4 here, and the same down here, pi D2 squared on 4, you get equals V1 times D1 squared on D2 squared, okay? And this is an important result because what it tells you is that if D1 is twice as big as D2, then this ratio, once you square it, becomes 4. So V2 equals 4V1, okay? And that's how I do this. I kind of did that in my head. I just multiplied this one by 4, okay? And that's going to be much faster. It'll save you time on a test or a quiz or anything that you need to do. Okay, anyway, geometry. Okay, let's zoom in way down here. And let's get our geometry. Okay, well, actually geometry, we just need to look at this. I'm going to set this as my datum. So z equals 0. So z1 equals 0, and z2 then is lowercase h. Okay, now you don't like that, right? Because you're like, well, I don't want to deal with lowercase h. Well, deal with it, okay? Something tells me that the lowercase h is going to find a way to go away. That's just what lowercase h's do. Okay, they're very hateful little creatures. Okay, so now we need, oh no, what is going on here? Okay, let's see. Is there a way? No. How do I zoom in and out? Oh. Maybe I'll go over here, I can zoom in and out. Okay, this is getting treacherous. We're running out of spaces for doing these things. Okay, so now we're going to do the manometer equation, okay, because we want to get hydrostatics in order to get our pressures. Okay, so let's see. All right. So the pressure at 1. Okay, so you should remember this from pretty early on. Okay, now we're going to go down. Plus gamma, that's the oil, H. Okay, now we're going to go from there down to here, plus gamma mercury times 3 feet. Son of a, 3 feet. Okay, now we're going to go back up all this way. Okay, minus gamma of the oil. I hate working down in this corner. Gamma of the oil times, well, we can't quite see it all. 3 feet plus capital H plus lowercase h equals pressure at 2. Okay. All right. Now I'm going to rearrange this in a special way. You've probably seen me do this before. So P2 minus P1, okay, so basically I'm going to take this P1, I'm going to move it over to the other side, and then I'm going to divide the whole thing by gamma naught, okay? And that's going to leave over here, so I'm going to divide both sides of the equation by gamma oil. H plus gamma Hg over gamma oil times 3 feet, minus 3 feet minus h minus lowercase h. Okay, so you see this capital H and that capital H will cancel, and we're left with P2 minus P1 over gamma naught, gamma oil, not naught, equals gamma Hg, which is 13.55 times gamma water, over gamma oil, which is, in this problem, 0.88 times the gamma of water, okay, times 3 feet minus 3 feet minus h. So P2 minus P1 over gamma oil equals, if you plug all that in, 43.36 feet minus h. Okay, cool. All right. So now we're going to come back over here, and I'm going to make one little adjustment to my original equation. Just something that we need to be aware of is that there needs to be an oil right there. Okay, the gamma that we're doing this in is the gamma of the flow. Okay, no other gammas. Okay, so the reason that I solve it like that, like this, is that I can plug it in here pretty easily. Okay, so at this point, this is a bit of a plug and chug. Okay, so what I'm going to do is I'm going to start rearranging things. Let's see here. Let's use white. Okay, so I'm going to have P2 minus P1 over gamma oil. So you see I brought this over to there. Okay, so that is on the right-hand side. All right, so get out of here. Okay, so basically we're going to, at this point, we can kind of rewrite the rest of this stuff. Z2 is over here. We note that Z1 is 0, so we don't need to rewrite that one. Okay, so the left-hand side is going to look like, let's see, there's just an alpha left, and the alpha's gone. Wait, did we check these alphas yet? We did not check these alphas yet. So let's go ahead and check these alphas just to be sure if alpha is 1. Okay, so we need to basically find out if the Reynolds number is greater than about 2,000 or 4,000. Okay, and that will make this alpha equal to 1. Okay, 1 question mark. Okay, so I'll go ahead and test it. I'll tell you right now it's going to be, but let's just go ahead and do it. So the velocity at point 1 is 6 point. I'm not going to worry about all the sig figs on this because it doesn't matter for Reynolds number calculations, and you'll see that in a second. Okay, the diameter is 1 foot. Okay, and the viscosity in this system of units is about like that. Okay, feet squared per second. Okay, so it is unitless. Okay, and if you do that calculation, you can see you're going to get 6.4 times 10 to the 5th. Okay, so this is turbulent. Okay, so that means alpha equals 1. Okay, approximately. Okay, now we could do it for the other one. I don't think it's really going to make a difference, but we'll go ahead and do it just to be sure. 25.5 feet per second. Okay, now we're going to go times a half a foot. Okay, divided by 10 to the negative 5th feet squared per second. Okay, so if we do all that, I'm just kind of doing this in my head. It's about, 13 on the top divided by 10 to the negative 5. So 1.3 times 10 to the 6th. Okay, more or less. Basically turbulent, much bigger than this 10 to the 3rd. Okay, we're at 10 to the 6th. Okay, so this is turbulent. Okay, notice it's unitless. I made sure all the units canceled out by putting feet and feet per second over feet squared per second. Okay, so we're going to come back down here. And so that means these alphas are going to go away, okay, because they're 1.0. You're not going to be able to see it if I write it right there, but, you get the idea. Okay, so anyway, pressure 1 on gamma got moved to the other side. Z is 0. Z1 is 0. We have V1 squared on 2G, okay, with a bar over it. Okay, on the right-hand side, we've got P2, we've already copied. Z2, we've copied. And now we need to add V2 squared on 2G. Okay, we got rid of the alpha because it's turbulent. Okay, both of these things go away for reasons outlined earlier. Okay, so at this point, we're ready to plug and chug. So bear with me. It's going to take me a few moments to just kind of fill this out. 6.3. I'll say it out loud as I go in case my handwriting makes no sense. Okay, over 2 times 32.2 feet per second. Feet per second. Oh, son of a... feet per second squared, okay, equals P1 minus P2 over gamma. So that's where I'm going to plug this in, okay, 43.36 feet minus lowercase h, okay, so this is going down here. Z2 is going to go right here. Z2 is lowercase h. Oh, look at that. The lowercase h is going away. We always hated you, and we were so glad to see you go. I don't mean that. I'm much nicer than that. And V2 squared is 25 point. I'm going to need to erase in a big way because this is in my way. Okay, get out of here, punks. Good for nothing. Okay. So 20. What just happened? Oh, okay. 25. 25.465 feet per second squared over 2 times 32.2 feet per second squared. Okay. Notice that these are all going to be in units of length. Oh, I forgot. Oh, how did I forget the whole point of all this? I forgot HP. HP. Okay, that's the whole point. That's what we're solving for. Okay, so if we solve all of this, I'm going to get HP plus, I'm going to put in this intermediate step. I know you probably hate me for it. Hopefully you do. 43.36 feet plus 52.80 feet. Okay, and I'm doing this because I want to make note of something. I'm going to get a color that will show up. Green is probably a good one. Blue is a good one. Okay, notice that the amount of energy leaving this system is a lot more than entered the system. Okay, it's kind of a combination of both the pressure and the elevation. Okay, and this is the velocity head. Okay, so if you compare that to what we had going into it, which was only velocity, and it wasn't very much velocity. So you can see that in order to get this much energy out, we're going to need the pump to supply a lot of energy, okay, because it has to overcome that energy gradient. Okay, how much energy? Well, we just figured it out, okay? So, well, it needs 52.80 feet, okay, in terms of head. And you may be more interested to know, well, what is that in, I don't know, horsepower or some kind of unit that we can get to? Well, that's the whole point of this question, right? So what we wanted to know was we wanted to know how much power does the pump supply to the fluid. Okay, so that's the fluid of oil. Okay, HPQ. Okay, so the gamma of the fluid is 0.88 times the gamma of water, 62.4 pounds per cubic foot. Okay, the head of the pump we solved for is 52.80 feet. And the Q is 5 cubic feet per second. Okay, that was given. Okay, so the work of the pump, or the power of the pump, the rate of work of the pump is, let's see here, 1.45 times 10 to the fourth foot-pounds per second. Okay, so notice we've got a torque per time. Okay, or work per time. Okay, and if you want that in horsepower, which a lot of things will, you take that number, you divide by 550, so that's the conversion rate, 550 foot-pounds per second per horsepower. And if you divide that, you get 26.4 HP, horsepower, okay? And a lot of times you just do that because this is a big number, okay? It's not really anything, okay? So that's the answer. We'll zoom out so we can get a good look at the carnage. That's what we've done today. I hope you're proud of yourself. Hopefully this one was better than the last one. Okay, have a good one. I hope y'all are, staying safe and happy and healthy. And remember that your health is more important than even fluid mechanics. I know it's hard to believe, but take care of yourselves. Know that I'm with you and that I love you and that, I will do what I can for you. So be easy. Gamma. Oh, slides now. Can I? Horrible. I have so much. cube.